Thank you. So before I start, I of course want to thank the conference organizers for putting together such a great program and for inviting such a diverse and fascinating group of people to talk to each other and present their ideas. So today I want to tell you a few things. So first I'll talk about some history of a search for deterministic models of quantum theory. Then I will segue into Bohmian mechanics and discuss weak measurement as a probe. And I will discuss how weak measurement can be used to probe various interesting quantum and subquantum features. And this relates to Howard's talk earlier, so that was a really wonderful introduction. And then I will conclude with a couple of thoughts. I would like to thank Ephraim Steinberg, who is hiding and preparing his talk, for getting me involved in this field of weak measurements and for getting me involved in this Bohmian trajectories experiment. And I would also like to thank Christoph Simon of the University of Calgary, with whom a lot of this entangled particles and other interesting quantum features work has been done. All right, so I guess the question that all of us have spent some time thinking about that are gathered here is the following. Is quantum mechanics the final theory? And you can consider possible answers to this question. One answer is yes, quantum mechanics is all there is. But if you don't believe that this is the case, you can further subdivide the question into the following three. So the first one is you can ask yourself, is quantum mechanics correct? That is, are there experiments whose results would be in contradiction with the predictions of quantum theory? And over the last couple of days, we've heard about many such ideas, many kinds of theories whose predictions will contradict that of quantum mechanics in certain limits. For example, on very small scales, or for very large energies, et cetera, et cetera. So there are many theories that postulate this, but as far as we know, there are no known experiments where this has been observed. So as far as we know, quantum mechanics is correct. The second question you can ask is quantum mechanics complete? That is, are there theories that are completely inconsistent with the predictions of quantum theory, but that also allow you to make greater predictions or more accurate predictions than that which quantum mechanics allows? And so this kind of theory would not be in direct contradiction with quantum mechanics as we know. So these kinds of theories have not been entirely excluded right now. But on the other hand, no one has found a theory that is more predictive and demonstrated such a more predictive experiment. And the last question is, are we thinking about quantum theory in the best way? So do we have the correct interpretation of quantum mechanics, even given the condition that the quantum theory as it stands right now has as much predictive power as any theory can ever have? So today I'm going to talk a bit about deterministic theories, in particular focusing on Bohmian mechanics as an example. So where does Bohmian mechanics fit into this three categories? So standard Bohmian mechanics, where you postulate that the distribution of particles is just equal to psi squared, is distinctly in the third category, where the particle position is not necessary to make the same predictions. But if you postulate that you could create a state where the distribution of Bohmian particles was not the wave function squared, then Bohmian mechanics would be in the second category. But that would have various other nasty implications like non-locality and other things like that. All right, so people have been trying to find a deterministic alternative or version of quantum mechanics for many years now. Most famously, this started with the EPR paper in 1935, which argued that quantum mechanics was incomplete. And their implication in that paper was that we should be looking for hidden variable theories, and in this case, local ones. Then, 3 years before, actually, von Neumann published the proof, or so-called proof, as it later turned out, that you could not create a deterministic hidden variable model of quantum theory. And then in 1952, Bohm published this theory that I'm going to be talking about, and this was inspired by de Broglie's Poilet wave, and it was highly non-local. So in 1964, Belden proved that every single hidden variable model had to be non-local in the same way that Bohm's model was. That if you had made all these predictions consistently with quantum mechanics, your theory had to have some feature of non-locality. So EPR's quest was not very successful. And I'm just going to obligatorily quote Bell, who wrote about the relationship between the von Neumann impossibility proof and the Bohmian mechanics, where he wrote that in 1952, I saw the impossible done. And then if you read the abstract of his paper, he says that morals are drawn. And if you actually read through the paper, the morals that he draws is he criticizes the tendency to only teach one interpretation of quantum theory. Even if this interpretation does not add any predictive power, it gives you a different way of looking at things. So that is the reason why it is interesting to look at quantum experiments from a different perspective. Okay, so suppose we really, really, really want a deterministic extension or version of quantum theory. So we've had 80 years since EPR, and people have come up with various conditions and requirements on such a theory. So the first one is that it has to satisfy Bell's theorem, so it has to have these non-local correlations. The second one is that it has to exhibit contextuality from Koken and Specker, and I will talk about that a little bit later. Then, 2 years ago, Kolbeck and Renner published this paper stating that no extension of quantum theory can have improved predictive power. So they argued that all theories had to be in the third category, according to my classification above. But if you read the paper, they have a caveat that states that if you have a theory which has superluminal signaling of whatever microscopic variables you have underlying your theory, then that it can still have greater predictive power than quantum theory. And then finally, last year there was this paper by PBR, which stated that the quantum state had to be real. And the sense in which it had to be real is that if you have a hidden variable theory, which has various parameters lambda of the theory, the wave function has to be uniquely determined by this set of hidden variables. So you could not have multiple wave functions corresponding to one underlying state of reality. So if you want to have some kind of deterministic extension of quantum theory, it has to satisfy these 4 criteria, and not surprisingly, Bohmian mechanics does exactly that. So here's my 1-slide experimentalist review of Bohmian mechanics. You take the wave function, you decompose it to a real and a phase part. And the probability is just the amplitude squared. And then you take Schrodinger's equation, and then it applies a Hamilton-Jacobi equation with a quantum potential that I don't write because I don't need it. And the second one is this continuity equation. And then you can define the Bohmian velocity through this expression, which is the probability current over the probability itself, or the gradient of the phase divided by the mass. Now, Howard correctly stated that there are many versions of this velocity, but this is by far the simplest one, and that is the one we are going to use here for reasons you will see in a second. So these 2 equations actually have nothing to do with Bohmian mechanics. These equations originate just as well out of standard quantum mechanics. They're just the conservation of probability within a given volume. The probability current flowing out of the volume has to equal the change in the probability density inside of this region. So what does Bohmian mechanics actually add? What it adds is the existence of a particle position that moves according to this velocity. That is the key addition of Bohmian mechanics, and this extra element of reality is what makes the theory have, in a sense, more predictive power if you knew this position. So that's what makes Bohmian mechanics, is identifying a real particle position, and this is the velocity that tells the particle how to move. So people that talk about Bohmian mechanics often show you Bohmian trajectories, but they don't always show you how you actually find these Bohmian trajectories. So I decided to put this slide in just to show you. So this is the double-slit experiment. This is the amplitude squared of the wave function. The particles come up from the bottom and travel upward, or you could think of this as the time axis, and this is the position. So we all know what the amplitude looks like of the wave function, but what does the phase of the wave function actually look like in this experiment? And if you calculate the phase, this is what it looks like. So in the regions before the particles start to interfere, down here, the phase is more or less uniform across each slit. But as you go to the top in this interference region, you see that there are these clear lines running through the phase. And these are sort of mini jumps in the phase, which Bohmian mechanics then identifies as locations that have a large value of the velocity. So this is a plot of the velocity. So if before the interference starts, the velocity is simply a divergence. So on the left side here, the particles are moving to the left. On the right side, they're moving to the right, as you would expect. But once you get to the interference region, in every dark region of the interference, the velocity is large. And it's very easy to understand why this has to be true, because the particle can only spend a small amount of time within each dark fringe of the interference. So it has to transit through it quickly, and hence it has to have a large velocity. And now all you do is you numerically or analytically integrate this, depending on how good you are at integration, and you obtain these trajectories, which we all have seen before. Okay. So this is going to be a very, very brief summary of weak measurement. Again, from an experimentalist perspective, it's going to have many fewer equations than what Howard have. You use a pointer with a large uncertainty relative to the strength of the measurement interaction, and that allows you to obtain a small amount of information about your system that you're measuring without creating collapse between without collapsing the state of the system. So you don't generate strong entanglement between the two objects. And this, as I will show you in a minute, and as Ephraim will talk about also later, can be used as a tool for probing and understanding subtle quantum features. Here's the standard von Neumann paradigm of measurement. You have your system, you have your pointer, and if the pointer is classical, so like this arrow, it doesn't matter how weak the interaction is, you will always obtain a definite outcome of the measurement. But in reality, pointers can also be quantum mechanical, and they can have some intrinsic width, so they can have a wave function of their own. And what you want is you want the evolution that connects the system and the pointer to give you only a small shift in the pointer's position or momentum, whatever you're using to measure the system. So the interaction time, t, times this coupling strength, chi, has to be small. So that's all weak measurement is if you're an experimentalist like me. And so this can be used for doing various cool quantum tricks, one of which is this direct measurement of the wave function done by Jeff Lundin 2 years ago. So this is an experimental setup. I will quickly explain what it does. So at the beginning, you prepare a state of the photon. So the wave function that they're measuring is the transverse wave function of a photon. So it can have phase gradients, jumps. It can have a double slit, which they didn't do, but in principle they could. And then what you do is you put a very small sliver of a half wave plate, which tags the photons that go through this position. So it's a weak measurement of the position, and it's weak because what you're doing is you're coupling the polarization state of the photon, which is the pointer, with its spatial position, which is what you're trying to measure. And then as you move the sliver around, you can extract both the real and the imaginary parts of the wave function. So this is the amplitude of the wave function. And here, the red part is the real part, and the blue part is the imaginary part, and the black curve is the resulting phase. So what they did for this experiment was put in a half wave plate, so there is a pi phase jump in the middle of the wave function. And as you can see, these kinds of weak measurements allow you to extract values of quantum systems directly. So normally, if you were measuring the quantum system, you could only obtain either the real or the imaginary part, but here you can obtain both with one setup. So that's why weak measurements are cool, and you can do other interesting things with them. I'll let Ephraim tell you more about that. So what I want to tell you about is this measurement of trajectories, and what this originates with is the ability to measure the position and the momentum of a particle, in scare quotes, simultaneously. So Howard, as you heard about already today, explained that if you do a weak measurement, so in his case, he did a weak measurement of the position at some time, and then a strong measurement of the position a very brief time later. That is mathematically equivalent to just doing a weak measurement of the momentum. So that is what you do. You do a weak measurement of the momentum, and it turns out that that just equals to the Bohmian velocity, very conveniently. And that means that by building such an experiment, you can actually measure the trajectories of quantum particles in the Bohmian perspective. So to emphasize this point, notice that when we published this result, the title was the average trajectories of single photons. And that is absolutely correct, because you can't actually measure the trajectory of a single photon or any single quantum particle. But here's the key point. If you believe in a deterministic model of quantum theory, if you truly believe that there's some deterministic behavior underlying quantum mechanics, such as the motion of the single particle along the Bohmian trajectory, then when you perform a measurement such as this, and you condition the measurement on the particles landing at some final position on your measurement device, that means that all the particles that got to this point traveled along exactly the same trajectory before they got to that point. And that means that whenever you perform such a weak measurement, and then you do an average over many particles, the average is actually equal to the real value of whatever you were trying to measure. So if you believe in a deterministic model of quantum theory, then these kinds of weak measurements can be used to extract real actual values of these hidden parameters. So that was my understanding of Howard's result, and that is what actually happened in the experiment. So let me again quickly explain what actually happens here for everyone's benefit. So what we do is we prepare a double slit using 2 fibers. So that answers the question. The output mode of a fiber is not strictly a Gaussian, but it's pretty close. Then we prepare a polarization state, which is going to be the pointer for our measurement. We perform the weak measurement by coupling the momentum of the photon to the polarization state. So photons that travel a little bit to the left experience a polarization shift in one direction. Photons that travel to the right experience a polarization shift in the other direction. And the change in polarization is very small, on the order of a few degrees. So that means that the measurement is weak, because the pointer itself has an uncertainty of roughly pi for the polarization of a photon. And then we perform some optics, so to let the photons evolve, and then we observe the patterns for the two polarization components. So here's what the momentum measurement actually looks like. So the red and the blue curves show the two components of the polarization. So they tell us, say, at this position, the particle was slightly more likely to be traveling to the right than to the left, because the blue curve is higher. And vice versa, here it's the opposite way. So by looking at the difference of these two curves and normalizing to their sum, you obtain the black points, which show this velocity distribution. And if you just calculate what the momentum at each position has to be in order to enforce probability conservation, just to make sure that the pattern evolves from one plane to the next in the correct way, you obtain the magenta curve, which agrees relatively well. So that's what we did. And then if you do this in many planes of the propagation of your photon, you can actually reconstruct the trajectory, and here's a little movie. Yes, it works. So this is the momentum value in each plane, and these trajectories get reconstructed. You're just numerically integrating. So basically, you assume that the particles that enter a given plane have whatever momentum, and you just do a straight line and then another straight line. So that actually leads to the accumulation of numerical errors, and that's why you see this bunching more than expected at the final plane. But it's not too bad. So if you take the probability distribution in the final plane and you compare it to the trajectories, you see that they bunch up in roughly the right areas. But notice that these trajectories are reconstructed using values that are propagated all the way from the beginning. You took the particles all the way from the beginning, and you took it over 6 meters of propagation into the far field of the interference. So this is the kind of thing you can do with weak measurements if you analyze the experiment in the context of Bohmian mechanics. Okay, so that was all for a single particle. So what interesting things can we do with, say, two particles? And this is an experiment that we proposed with Christoph, and it has not yet been done, but Ephraim is working hard on it, as far as I know. So the idea is that you take a source of entangled pairs, and you send it off into two locations such that either both particles go through the upper slit, or both particles go through the lower slit. And then on one side of the experiment, you have this phase plate, which you can adjust as the experiment. So think of this as Alice, and this is Bob, in the usual terminology. And if you look at the biphoton wave function, it looks like this. It has two spots which are offset from each other. This is both particles going through the upper slit, and this is both particles going through the lower slit. And if you let this pattern evolve, it gives you these interference fringes. But keep in mind that these are not local interference fringes. If you observe the position of only the first particle, you will not see an interference pattern, because you can't, because this particle is entangled with this particle. But what you can see is if you detect the particles and you correlate the outcomes of the measurements, the pattern will actually depend on this phase. So you have this non-local interference whose behavior depends on the phase on this one side, which means that so if you now go into a deterministic theory such as Bohmian mechanics, this phase, changing this phase, will have an immediate effect on the trajectories on this side in an instantaneous, non-local, spooky action at a distance kind of way, the kind of way that Einstein was not very fond of. So here's what the idea is, just to do the same trajectory measurements that we did before, and then what would we observe if we did the experiment. So here's what would happen. So let's just focus on these three lines and these three lines. So here I'm assuming that the initial position of particle B is 4 and the particle A is 3. If this phase is set to 0, the two particles will follow the trajectory given by the red line. But if you say change this phase to pi all of a sudden, then the trajectories will be these blue dashed lines. So if you actually reconstruct the trajectories as a function of this phase, you would observe these highly non-local effects, which you expect from Bohmian mechanics, and as any deterministic hidden variable model also has to exhibit. And this is just a plot that shows a very similar effect. So this is one of these transverse velocity plots as a function of phase, and you see that there's the features in the middle change rapidly as you change the phase on only one side. So this is the velocity of this particle, depending on what you do with the phase on this side. And what keeps this from being a signaling non-locality is that these measurements are all conditional on finding this particle at a given point and this particle at a given point. So in order to reconstruct something like this, you actually need to know where this particle landed. So that way you don't have superluminal communication. Okay, so now that we've got the non-local trajectories covered, what else can we think of doing with such an experiment? One thing we can do is just doing a Bell test, which should be conceptually simpler. All you need to do is you create one of these entangled pairs, and you send it to a Bell state analyzer, which is just a faceplate and a variable reflector, which transforms this state into some linear superposition, this state in some linear superposition. And then to violate a Bell inequality, what you need to do is you need to change these values quickly and then these values quickly. And then you look at the correlations depending on what values you set to this. And what would happen in a Bohmian analysis of such an experiment is when you change the settings on this side, you would immediately see the trajectories of particles on this side change to make sure that all the correlations you expect are observed. The problem, though, is that doing trajectory measurement inside of a device such as a beam splitter is difficult. So we haven't come up with a good, viable experimental way of doing this. But you could conceivably imagine doing this kind of experiment using, for example, electrons or atoms, where you can do beam splitters without a physical object there. But conceptually, this is possible. Okay, another thing you can think about is contextuality. So in 1967, Koken and Specker proved that hidden variable theories have to be contextual. So what does that mean? So imagine that your theory has a set of variables lambda, and then you have some operator A, and you want to predict what the measurement outcome will be for operator A given these hidden variables lambda. And what the theorem shows is that you cannot uniquely determine this value, A of lambda, unless you also know what other observables are being measured simultaneously with A. So if you measure A, B, and C, you won't always get the same measurement result as if you measure A, D, and E, even for the same values of the hidden variables lambda. So one way to think about this is that the setting of the experimental apparatus is part of the variables you need to specify to predict the results of measurements deterministically. And this is actually related to this von Neumann proof from 1932, where von Neumann incorrectly assumed that the prediction of a hidden variable theory for the measurement A plus B is equal to the prediction for A plus the prediction for B. And that is a non-contextual equality, so it is not indeed correct. And that is why the von Neumann proof failed and why Bell was able to see the impossible done. Okay, so all you need to do, again, to do this kind of experiment is you construct a Q-tert analyzer, because to show contextual behavior, you need a three-dimensional Hilbert space. And if we want to analyze things in a Bohmian perspective, then we want everything to be in position space because it's nice and simple, and we have, at least in principle, a way to measure the trajectories, which are these hidden parameters of the theory. So what you do is you construct this Q-tert analyzer, which takes 3 possible inputs and converts them to 3 possible outputs, and these devices just implement an arbitrary unitary transformation. So in this kind of setup, it turns out that if you measure 0 or 2, so if you measure projecting onto this state or this state, you will have non-contextual behavior. It won't matter if you measure 0 and 1 plus 2, or 0 and 1 minus 2, it doesn't matter what other measurements you do if you're just measuring projection onto 0. And in the Bohmian perspective, that's easy to understand, because if your particle was going to go into this detector, it's just going to go straight. It's not going to go through any other parts of the interferometer. Similarly, if you're measuring the 2 basis, then the particle just goes around this side and goes straight in the detector. But if you want to measure 1, then the measurement will be contextual, in the sense that the trajectories that result in a click of 1 will depend on what other variables you're measuring together with variable 1. And so if we do a trajectory measurement in this whole region, then we can again directly observe the trajectories change as we change the measurement settings. So the way you change the measurement settings is you actually have to change what these beam splitters do. And that is how you obtain the changing trajectories, so it's not entirely surprising that contextuality arises in a theory like Bohmian mechanics. Okay, so the last thing I want to talk about is this issue of surrealistic Bohm trajectories. So in '92, there was this paper which argued that Bohmian trajectories were surrealistic. And the argument was based on the following simple experiment, which was to build a double slit and then do a which-way measurement. And then they argued that in the Bohmian perspective, the particle could never cross this midline between the 2 slits. So if a particle went through this slit, the detector on the screen would always have to click in the upper half, and in the bottom slit, it would have to click on the bottom half. But that is obviously false. You could, if you know that the particle went through this slit, then it just diffracts out, and it doesn't really care about the Bohmian trajectory, and it can sometimes land in the bottom half of the screen. So that was their argument for for Bohmian trajectories being surrealistic and predicting, say, incorrect things, like the Bohmian particle going through this slit when actually it was this detector that clicked. So that's bad. And before I came to the conference, I was pretty confident of what the answer would be. But then I had a lengthy debate with Howard and Ephraim, and now I'm confused. So I'm just going to pose this as a question. So what will happen when you measure the trajectory on the other side of the slits? So one possibility, if you do a strong measurement of which slit the particle went through, is that you will just see the single slit trajectories for each slit. That makes sense. Another possibility is that if you do a strong measurement of which slit the particle went through, you might see these Bohmian trajectories. Or another possibility is if you do the measurement weakly enough, such that interference is still observed, you will still see the double slit interference pattern trajectories. So I'm not confident enough to claim that any of these is actually what you will see. So that's something up still for discussion. Okay, so just to summarize, deterministic extensions to quantum mechanics are strongly constrained by well-known results, but are appealing because our intuition tells us that things should be somewhat deterministic. Weak measurement can be used as a probe of quantum features, and if you believe in a deterministic theory, they can be also used to probe subquantum features, such as Bohmian trajectories. And the idea is that by combining the paradigm of a weak measurement and a deterministic theory, you can piece together a different perspective on many quantum behaviors. Thank you.
It was a wonderful talk, and we have time for a couple of questions. Please, are there any comments or questions?
Nice talk, Boris.
Thank you.
I will tell you, if you read my paper in Physica Scripta, you'll see the answer to the bone trajectories is this one here on the left.
This one?
Yeah. So
Okay.
if you don't get that one, please don't come and visit me.
So what if you do a weak measurement, though?
You will see that.
Okay.
Professor, here, first. Professor Ozawa.
I have read von Neumann's proof very carefully. Then I found that he assumed that you can collect the objects with the same value of hidden variable. If you can do that, von Neumann proof is not nonsense. Because if you collect the ensemble according to the value of hidden variable, then this ensemble is just the statistical ensemble. And for this statistical ensemble, the additivity of expectation is naturally whole. So even A and B are non-commutative. You can have this ensemble from the hidden variable. Von Neumann's proof works. Then a question arises, given hidden variable theory, how do you guarantee that you cannot correct the ensemble according to the value of hidden variable?
So the question is whether you can, in principle, prepare the hidden variable to be some fixed value. Like, if you want to prepare lambda is equal to 1, for example.
Yeah, if you say that this is a hidden variable and they escape von Neumann's impossibility proof, then if your theory can construct the ensemble with uniform values of the hidden variable, then your hidden variable theory should contradict von Neumann's proof.
Well, if you could prepare, so I'm not familiar with the general situation for an arbitrary hidden variable theory, but in Bohmian mechanics, if you prepare such an ensemble, then you're going to violate everything left and right.
Okay.
You'll have non-local superluminal signaling. You'll observe all sorts of crazy things.
Okay, so you explicit, you cannot correct the such kind of ensemble from the Bohm theory.
There is no indication that we can. If someone could do that, that would be a really interesting result. Yes.
Okay, another question that Bell constitutes the hidden variable theory for two-dimensional case.
Yes, of course. That's
but,
why you need a 3D case here.
Yeah, but I don't know that there's no explicit proof. From his theory, you cannot make statistical ensemble with the uniform variable, hidden variable. How do you think?
I think that this is like an extra statement about there's no fundamental law inside of quantum mechanics itself which says that you cannot prepare such ensembles. Quantum mechanics itself does not exclude the possibility of making ensembles that don't have, say, the standard distribution according to Bohmian mechanics. This is an extra statement about the nature of reality that we have to make based on experiments that show that, say, you don't violate non-locality, you have all these constraints on how things work.
But from my point of view, this problem is very crucial because you don't have any proof about this Bell's model is complete. You don't have any proof Bell's model is consistent with usual quantum mechanics. He just proved that some expectation is coincide. But all the prediction from his model is consistent with quantum mechanics. It's open, I think.
I mean, if you have two models which predict the same thing, then they're mathematically equivalent.
No, the quantum mechanics predicts the correlation, but Bell's argument doesn't touch the correlation possibly predicted from the quantum mechanics.
So what's the question?
Like weak values. Because the weak value can be predicted by quantum mechanics. But Bell's argument didn't touch the predictability of the weak value from his model.
It's a good point, but definitely worth thinking about. That's why we haven't yet written a paper about this.
Theo, we need a question, or can we move on? Okay.
Yeah,
one quick one.
Just a simple question. You've been studying this subject for a while. Do you have some intuition on real trajectories?
Well, what do you mean by real?
Well, the particles go.
If you choose to believe that these trajectories are real, then they're real.
No, and you don't. These are statistical trajectories, but now the real trajectories. Do you have some intuition about that?
I mean, they're real if you believe in Bohmian mechanics, otherwise they're statistical trajectories.
Yes.
That's what it is.
Okay,
and I mean, in standard quantum mechanics, there's no room for real trajectories.
No, but we live in the world, huh?
So.
We live in the world.
Well, we can't know. At least we don't know a way of knowing. Not yet.
Okay. I think on ontology, we pass on for dinner conversation.
Exactly.
Right.